Hello. Yeah, welcome to session number 12 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam, and in this series, I'm going to continue talking about passives. And once I'm done with the most important passives, I will move on to active devices. So next in the passive devices is something called a coupler, and the coupling can be a edge coupling. So what do I mean by edge coupling? So for example, there are two lines which are like this, and then there is a gap in between the two lines that would be called edge coupled, or it can be broadside coupled, like for example, the signal runs for a certain length together on both the lines. That will be called broadside coupling, right? So now again, there are two categories of people. One is called a designer, and the other one is called a application engineer. So what a application engineer will do is he will put these two in ADS and run an optimizer on width and the spacing S. While a designer won't do that. Designer will write the equation to have an exact design, right? Okay, so let's specify some of the dimensions. So let's say that these two lines are running together for a length of L, right? And then they have a space of S. So let's just mark them. Insert shapes. So let's say it is running for a length of L. Okay, so it is running for the length of L, and this L is usually lambda by 4, right? So I'm going to put here L. So this is length. This is the length of the line, usually lambda by 4. That's what we are going to expect. Then there's something called the width. So let me make sure and I'm recording. Yeah, I'm recording. Okay, so then let's say we denote width by W. Okay, so that is the width of this line. So let me show you what that W is. Okay, so if I was to do from here to here, that will be called the width of the line. Okay, so that's the width of the line, and most probably these are symmetric, so that's why, and now this theory can be expanded to, more than two couplers, like, more than two lines coupled together. You can put in like even number of lines, like n even number of lines. You can put n times of two, right? So that will result in a same coupler, right? It's just that the most important parameter over here is the gap, right, and the width for impedance matching. So this is W and also this is W, and then you have this gap which I will call as S. Okay, so this distance is called S. So that is going to be the design of the coupler. So I'm doing a very simple coupler here. Okay, so now what happens is there is a technique of analyzing such coupled circuits, which is called even and odd mode technique. Now what you do is, for example, let's assume that you are putting signals on both the lines, right? And these two signals are in phase. So that's an even mode, right? That means that if there is a capacitance between the two lines, let's say is C12, right? So let me just copy this. So a capacitance between two lines is C12. So let's say insert equations. Okay, so I'm talking about capacitance between the lines as C12. C12. Correct. So this is the capacitance between the two lines, and let's say C11 is the capacitance of each line, right? And C22 is the capacitance. So basically, if the two lines are symmetric, then C11 equal to C22. So what I mean by that is, let me put here a model. So I'm talking about the even mode. So you got C11, right? So the model would look like this. and C22. And I'll explain you what happens in even mode. So this is not a even mode. I'm putting just a generic diagram of coupling, a capacitive coupling, right? Okay, so what's going to happen is the following, that this line had its properties, format shape, and line, I want to do a dotted line, something of this nature. Okay, so what's going to happen is, because the all the signals everywhere on any point, all the signals are basically in the same phase, then the E field between the two planes is canceling out, right? It doesn't exist, right? So then this capacitance C12 doesn't exist, and what you have is only C11 or C22, right? Okay, or C11 is will be equal to C22 because these two lines are symmetric, and the overall capacitance will be twice of this, isn't it? So the overall capacitance would be twice of that in the whole system. Okay, so uh, so if I was to write the equation for this capacitance, right, per unit length, so I'm not assuming length in the picture, and W is the width, S is the gap, right? So C11, so let me write it down. C11 would be equal to epsilon times, so it will be epsilon R. So let's see, where's the equation gone? Is equal to uh, epsilon R. So let's put here epsilon. No confusions. Where is epsilon? Uh, Sorry for the delay. I can consider this as epsilon. Epsilon R and epsilon 0. Sorry. Okay. Times of W divided by L, isn't it? So this whole thing by L, and this L, okay, basically I have to assume what you call the fringing capacitance, right? So a part of it is because of the depth, and a part of it is because of the gap. So the part of it which is because of the gap, I'm interested in that. So what I'll do is I will do B is the, so let's say H is the height, H minus S. Okay, so this would be the capacitance, and I'm going to consider twice of that as the overall capacitance. So I will say C even mode is going to be twice of that. Okay, so this is your even mode capacitance, and then even mode impedance, right, would be Z0E. So it will be ZOE or Z0E. Right. Z0E would be equal to 1 over Vp times of CE, right? 1 divided by Vp times of V, where Vp is the phase velocity. Okay. Or you can say it is Z of free space divided by C. Okay. Now, okay, Vp, sorry. So it will be Vp times of CE. See. And second thing to note is, okay, so this is for the even mode. Now, what happens for the odd mode, right? So the odd mode is going to look something similar. So in odd mode, what's happening is they are differential. So basically, the field is out twice, right? And when you do a superposition, then you have basically just the field just the wave, right? And so we have just broken the circuit into even and odd mode, but the whole point is that some superposition of that would result in the circuit uh, response to the signal. Now, so in that case, this capacitance would become twice, isn't it? So let's do solid line, is it? What? It should respond to a solid line, isn't it? Okay, we have done it through that. Okay, so in that case, this will be twice because the field is twice now. So this is just a mathematical convention, right? We had an even mode and now we have an odd mode, right? Control C, Control V. And for this, you can refer to any basic book, like for example, David M. Poshar. You will know the technique of this even and odd mode. It's a straightforward thing. And in between, there is going to be a ground, right? Okay, so this is the equivalent circuit for the odd mode. So, so this is the odd mode. Okay, so this is the odd mode circuit. So I will write it down here. So this is for even mode. So this is for the even mode. Sorry. And then for the odd mode, you have this circuit. And I'll write the equation for odd mode. Okay, for odd mode, CO would be C11. So it will be for odd mode, it will be this plus twice of, sorry, what is it trying to do? Okay, plus twice of, uh, this is capacitance, right? Okay, uh, twice of, okay, let me write it down. W, so this term would be constant. Okay, so now this capacitance is because of the spacing only, right? So if this is because of the spacing only, and this is going to be twice of C11, right? So this will be hang on, Control C, Control V, and here I will do an S. Okay, so this would be that, and the phase velocity for even as well as odd mode is the same. Then I can simply write the odd mode impedance to be ZOO, Z0O is VPCO, APCO. Okay, so now the thing is that we have a simple theory. For even mode, there is no coupling between the two lines, and the overall capacitance is because of the width and the length. The odd mode, there is a capacitance not only because of the capacitance to ground, but also because of the capacitance between the two lines, because the two signals are 180 degrees out now, and the field is twice now, E is twice, so that's why the capacitance looks twice, and that depends on the spacing here. In this case, it depends on the height minus the spacing. So we are taking out the fraction which is because of the height and the fraction which is because of the spacing. So that's there. Okay, so now we have the even odd mode capacitances and we have even odd mode models. We know the even mode impedance and odd mode impedance. And some more facts are that Z or Z0, okay, so Z0 would be equal to square root of or geometric mean of ZOE and ZOO, right? So I can put here that this is going to be the geometric mean of ZOE and ZOO. Okay, Z0E and ZOO. 0. Oh, okay. So this is going to be the impedance, right? Now, some more things are there. Okay. So let's say I number the ports also here. So insert. So I will copy any one of these. For example, this one. Okay. So this is P1. So basically this is port P1. Okay. So this is P1. Then we have P2. Okay. And then we have P3. And we have P4. Right. So and we have P4. Okay. So in this case, I can design for a coupling between P1 and P4. And then, so I have got these parameters. If I say P2 by P1, okay, so that will be a through coefficient. So I can write that as insert. So P2 by P1. P2 by P1. Okay, so this would be you can do a 20 log in case of voltage, you can do 10 log in case of power, right? So it is, if it is power, it is 10 log 10 of that, and it would be like a negative number, and it will really depend on what is the coupling, right? So the next thing is the coupling coefficient C. So let's put this one as 10 log 10 of, because I'm considering power 10 times of, sorry, I want to work with equation, 10 times of log 10 of, so log 10 of, okay, this number. And then I can have the same thing as a coupling coefficient C. Okay, so the coupling coefficient C would be equal to 10 log 10 of P4 by P1. Okay, and it will be again a negative number, and it can be like minus 10 dB, minus 3 dB, minus whatever you want to design for. So that's C. Okay, so C is in dB here, right? So C as a pure number would be basically C by 10. Okay, 10 raised to C by 10, right? And it's a negative number, right? So it can be 10 raised to 10 minus 10 by 10. Okay, that will be equal to P4 by P1, right? And the next thing is called the directional constant, which is going to be P3 by P1. P3 by P1, it's again a negative number. So now whatever is put into port 1 goes out through port 4 by a certain attenuation, and port 3 by certain attenuation, and port 2 by certain insertion. So the summation of all the 3 port power should be equal to the power put into port 1. That's basically the passivity of the structure, right? So what goes through between P1 and P2 would be what is put in P1 minus what goes out in P4 minus what goes out in P3. So that would be the power going through. Okay, so this is a passive structure, so the S parameter now would be 1, right? So let's go ahead and design this, right? So the design is very simple, and I'm going to use the same LTCC substrate. All we have to do is determine these capacitances for given impedance and given coupling, right? Not yeah, so for a given impedance Z0 and given coupling, I have to find out these C11, C22, which is same as C, and then C12. So, and based on that, I have to size the width and the spacing between the lines. So that would be a very simple design, right? So let's put this aside. Let's go here and write some equations. And these equations are going to be empirical. You can directly derive from here. Actually, you can derive from here, and they will be very accurate by derivation. But you are assuming a TEM mode. If you assume a quasi-TEM mode because of the fringing, then these equations are going to be slightly incorrect. So what I'm going to write is an empirical equation is correcting those quasi-TEM effects into the equations, and that way you will have a coupler which would be kind of exact, and again, if you are an application guy, you can always put a optimizer and on the width and the spacing, and then put a goal on the return loss, and you know and a coupling coefficient and directivity, and then you can get this, right? But then you are an application engineer, you are not a designer. So let's try to be a designer, not an application engineer. Okay, so I'm going to go here and say new this thing, and I will say file save. I will say coupler design, and this template can be used for any coupling coefficient, right, and any frequency. So that's what I'm going to do. Okay, so for equation, the first thing I'm going to put in here is height in microns, height in micrometers. So this height in micrometer is equal to, let's say I'm going to consider the height to be 297 into 2. So basically I'm going to consider a substrate. Let's consider a substrate here. Where is our substrate? This is our substrate. So 97 plus 97. So that is going to be 194. Isn't it? 9 to say 18, 14, 194, right? So the height would be 194. So my ground plane is on M5 while my structure is on M7. Okay, so we are clear with that. Okay, so now I'm going to say 194 is my height in micron, and then the height in meters is going to be 194. Height in meters is going to be 194 into 1e minus 6. So this would be the height in meters, correct? And then I have a frequency of design, let's say is 10 gigahertz, right? So frequency of design is f naught, okay, equal to 10 gigahertz, correct? Then let's say the coupling coefficient to start with is 10, okay, or minus 10, what you say, minus 10, right? So let's say I put this as ATTN or ATT or AT. AT is equal to minus 10, correct? So in pure number, the coupling coefficient would be, in pure number, the coupling coefficient C would be equal to 10 raised to something by something, that will be AT divided by 10. So this is in terms of power, right? Okay, so that's your coupling coefficient. Next is I'm going to have an epsilon r. So in my case, I will say ER, because what's happening is if I light a large number, unless it's conflicting with something, 5.92, it'll tell me if it is conflicting. So it is not conflicting. So ER is okay. Okay, if I want, I can make it a small ER. Okay, so that's done. Next is I want to have ZOE. Okay, so now if you know the circuit theory, right? So we have covered that, right? So you can write impedance in terms of gamma, right? So what is going to happen is 1 plus gamma divided by 1 minus gamma is the normalized impedance, isn't it? Right? I hope you remember the theory from the previous sections, or you can repeat it, right? So I'm going to write that, okay, in terms of, okay, so I'm going to write that as ZOE. So I will say ZOE. So even mode impedance is going to be Z0 times of something, and this something is something divided by something, right? And Z0 times of SQRT of something by something, right? And that is 1 plus C by 1 minus C. That's what we are attempting, 1 plus C divided by 1 minus C. Okay, so when we deal in terms of power, I don't have a square root. Okay, so again, so that's what it is, right? Okay, what has happened here? Something by something, and C is done. Z0 is not specified, right? So we are designing for 50 ohm. Z0 is equal to 50. So we are designing for 50 ohm. That's at the top. Okay, so now this is okay. And then we have Z odd mode because it is 180-degree out, right? So I should put here Z0E. Okay, and this is Z0O will be equal to 1 minus C by 1 plus C. So e raised to pi on gamma will result in the reversing of the sign, right? E raised to minus pi. Okay, so that is why this plus minus is reversed. Okay, so now the empirical portion comes. Okay, so I would have A would be equal to Z0 divided by 60, right? Times of square root of something, SQRT of something, which is going to be Fs plus 1. So you have seen this equation in antenna also, right? Or ER plus 1, right? Because what you have is a effective. So this is a quasi TEM. So I'm trying to compute the effective epsilon r in the equation itself. Okay, plus epsilon r minus 1. So same thing you have seen in antennas, right? So where I did a epsilon r separately. So that's okay. So plus er minus 1 bracket close divided by er plus 1 divided by er plus 1 bracket close times of this is from the antenna fringing stuff, right? So we did the same stuff for that. uh, Plus divided by er bracket close. Okay, so that's that. Then ZOSE, so it's an intermediate number, so don't worry about that. So ZOSE, ZOSE, right? ZOSE is ZOE by 2. E 2, correct. And ZOOE, OOE, sorry, ZOSE and ZOSO is just the half of ZOE by 2. Okay, now I'll find out same equation, exactly same equation. So I'll copy this equation and I'll say this is ASE and ASO. ASE is equal to ZSE, Z0SE by 60, right? Z0SE by 60 square root of ER plus 1 by 2, ER minus 1 by ER plus 1 by, and the remaining equations remain the same, right? And then Control C, Control V. ZSO is ZOSO. Okay, that's done. And then W by H. So this is the ratio of width to height. Okay, so W by H, W by HSE would be equal to pi by 8, right? 8 times 8 times of exp of ASE, exponential of ASE, and where is this ASE? ASE, exponential of ASE, close this whole thing divided by exponential of twice of ASE, exponential of twice of ASE. Okay, exponential of twice of ASE minus 2 bracket close, minus 2 bracket close, and this is divide by, not dot, so this is divide by, mistake. I'm going horrible. There has to be a bracket also. So it is going to be 8 times of EXE ASE divided by E raised to Okay, then control V. This is going to be ASO, ASO, ASO. So that's done. Correct. And then I will go spacing to the height ratio. Okay, spacing to the height ratio. So I will do S divided by H, S by H. Okay, so if I write this in microns, height in microns, right? So let's do this as 1 divided by pi, 1 by pi times of a cos h, cos h, 1 by pi times of a cos h of something, which is something by something, cos of h times of pi by 2, pi by 2 into WHSE, WHSE plus something open, cos h of pi by 2 times of W divided by WHSO, right? Bracket close, minus 2 bracket close. So this whole thing is a cos h divided by cos of something, so cos of h of pi by 2, pi by 2 times of HSO times of WHSO, right? Cos of that, right? Divided by 2 times of that. Okay, so minus cos hyperbolic of pi by 2 times of W divided by HSE, bracket close for cos, bracket close for this, and there is a third bracket close. Okay, so let's see. It is 1 by pi times of a cos h of brackets, cos h of this plus cos h of this divided by, okay, so do 1 1 1 1 1 minus divided by cos hyperbolic of pi by 2 times of WHSO minus cos h of pi by times of W underscore HC. Okay, so here there is a problem. Okay, so there was a imbalance of brackets, so that's fine. So this is S by H. Then G, okay, another equation. G is equal to cos H of pi by 2 times of, or pi times of S by H. Pi times of S by H, right? Okay, so that's G. And then D, okay, so D would be the effective distance. Okay, D would be cos of H of something, cos of H of something, which is pi by 2. Pi by 2 times of W by HSE, bracket close, and bracket close, bracket close, multiply by bracket open G plus 1 and plus G minus 1 time divided by 2. Okay, and then you have W by H, which is the width to the height. So W by H would be equal to 1 divided by pi times of A cos H of D minus SH, isn't it? What happened? 1 by A cos H of D, capital S. Okay, then you have W, so the length of the line is going to be quarter wave. So length, LEN, would be equal to C0, which is again 1 over square root of omega naught epsilon naught, and this is going to be a 4 lambda by 4, right? So divided by 4 times of frequency f naught, right? C velocity equal to wavelength into frequency, right? So wavelength will be equal to velocity by frequency, and then there will be a square root of, so the Vp will be the square root of SQRT of epsilon r, isn't it? Right, so square root of epsilon r, so that would be your length, correct? And this length would be in meters, isn't it? So the length in microns, so length in micrometer would be multiply with 1e6, so this will be in micrometer. The length is in micrometers now. And then we have got W and spacing S. Okay, so I'll just multiply with the H in microns, right? So let's just display these numbers. So what I'm interested in is I want to look at ZOE and Z. So I want to look at ZOE, Z0E. So this is even mode, this is odd mode. So this is 55 ohm and 45 ohms. for a 10 dB coupling. So that makes sense. Then I have S by H. So I'm interested in S by H, which is 24.245 times. And then I'm interested in, okay, don't worry about this, W by H, right? So equation, I'm interested in W by H. W by H, that's 1.706 times, right? And then I'm interested in the length in microns. So I'm interested in the length in microns. This is length in microns. Okay, so it is 3080. So if you remember, on a 97 micron substrate, we had 3832, right? Now on a 194 substrate, 194 micron, right? Uh, I have this as 3080, right? Now the next thing is width. So the width of the trace will be this thing. So if I say width in micrometer will be equal to W by H into H in micrometer. W by H into H in micrometer, correct? And similarly, I would have length in micrometer of the lines, right? So spacing in micrometer, and that spacing is W by S by H times of H. So that's going to be the spacing. So let's look at the width and the spacing equation. So I'm going to look at the width in micrometer, and I'm going to look at the spacing in micrometer. So that is spacing in micrometer. Okay, so the width is 330 micron and the spacing is 47.6, right? Okay, so this should give me a coupling coefficient of minus 10 dB. So this is my design. So let's go ahead and do its layout, right? The height is 194, right? Height is 194. So how I will lay this out is the following. Okay, let's go to a new slide. Okay, so the way I'm going to lay this out would be, let's consider this. Okay, so here, insert shape this guy. So I just want half of this, right? So here, sorry, it's this and it's this. So that's the half of it. How come this is white color? Okay, so that's the half of it. Okay, and then I am going to, the same way I'm going to lay it out also, right? So I have a certain 50 ohm. So I'm going to compute what is a 50 ohm. Okay, so the next thing I'm going to compute is a 50 ohm. Okay, so this is going to be like this, and this length is going to be, so this is the width. So I'm going to repeat this structure. A second, edit, group, and Control C, Control V, and then I'm going to flip this out. Flip vertical. Okay, so this would be the overall stuff, isn't it? Okay, so now what do we have? Okay, we have these extensions which are 50 ohm and they should be as small as possible, right? And I would keep it like 500 micron or maybe 1000 micron. Actually, this is just for adjusting your connector. So whatever is the pin length, you can keep it over there, right? And it has to be 50 ohm. So I'll go to line cal and make sure that, so if I go to any lines and I go to anything with schematic. So I'm going to go to the line cal tool, uh, line calculator, line cal. Okay, so what do I have here? I have 100 and so I have a epsilon of 5.92, correct? And I have a height of 194 microns, right? I have a height of 194 micrometers. Okay, and then I have a thickness of 9 microns, 9 micrometer. Sorry, so let's put here micrometer. Okay, 9 micrometer, and conductivity is 6.17. Okay, or it can be 5.85, 5.68. Okay, and then this is 0.2. Okay, now I'm all set, isn't it? And frequency I'm designing is 10 gigahertz, and I want a section of line which is roughly 45 degrees, right? And I want this to be a 50 ohm line, and I want the result in micrometers, and micrometers. Now, before I do this, I want you to guess of on a 97 micron. Okay, the line was how much wide? Uh, the line was 139 wide, 139 micrometer. Now, in case of twice the height, the capacitance is halved, so the inductance has to halve. Means the size, the line has to become fatter, isn't it? So it will be U 285 and 285 and 1827. 285 and 1827. So I'm looking at 50 ohm as 285 and 1827. 1827. Okay, so this is going to be your 50 ohm line, and then I have a line which is going to be, so don't worry about this now. No. Okay, so I'm interested in this, so now let me label it. So this is going to be 285. So this width, sorry about this. Um, I'm not so quick. Okay, so this width is 285. Insert text 285, correct? And then, so I'm going to keep this as 285. And then this length up to the half. Okay, so I am going to go here. So, okay, up to this point. So don't worry about how I do it. Okay, so up to this point, I am going to have this thing as, so I'm just going to rotate it. So from here to here, I'm going to keep this as, what is it? 1827, right? 1827. And really depends on how long is the pin of your connector, right? 1827 I'll keep. These are rough numbers because it doesn't matter on this. 1827, right? So this will be 1827. So I'm going to do this as 1827. Correct? So this will be 1827, and then this gap is going to be 47 or 48. Okay, so for, yeah, let's keep it 48. How does it matter? Come on. Okay, So this gap is 48, isn't it? So this gap, I'll adjust this slightly. It will be very accurate, but I might adjust this slightly, because you know what happens is, if you want a certain bandwidth and you specify the worst coupling is minus 10 dB, right? So you might keep them closer. Or if you want to say the best coupling is minus 10, so you want to keep it that way. So you decide what you want to keep. So 48 is my number, 48 micron. And then this width. Okay, so if this is there, so then this width, right? So let me put an arrow, or maybe the same arrow, right? So this width will be equal to, this width will be equal to how much? 330. See, 30. So this width I'll keep as 330. 330. Correct? And then the other thing is just going to be the repetition, right? So if I have 1827 minus 330, right? So I have a calculator here. 1827 minus 330. Okay, 1497. So this is going to be 1497. So let me pick up. So here, so this distance is 1497. So we will be very close to what we are trying to target, I assume. Okay, so this is going to give me a coupler, and let's just put this also. So this is 285, right? So this length, let's see how much is this length. This length is 3080, 3080, isn't it? 3080. So this length is 3080. So why am I doing this maths? The reason I'm doing this maths is then the layout becomes very simple if I do this math in advance. Okay, so this is 3080, isn't it? So this is going to be 3080. Correct. And then that means, so if this is 3080 and the other side is also 285, isn't it? So the other side is also 285, right? Okay, so I would have 380 into 285 into 2. So I will have clear 285 multiplied by 2 plus 3080. So it will be 3650. So the overall will be okay. So this will be 3000. 3000. How much is it? Calculator. 3650. 3650. Done. So all I need is a rectangle, which is 3650 and 1827, right? So let's do that. Height of the substrate is 194. Thickness of the metal is 9 micrometer. Correct? Lower one is your that thing. So there is already a directional coupler, but this is at a different frequency. So I'm going to make a new project in mm, and I'm going to call this 9 to 11 is okay, and say design close, and sorry view all. What has happened here? I'm looking at the top view. Okay, so there it is. So first of all, I just want to put in here dimensions here. Let's go to let's go to my drawing. Okay, so this is that. Then the overall size of this would be, so I'm going to put a ground plane, isn't it? Okay, so let's first draw the structure and then I'll put the ground plane around it, isn't it? Okay, so I'm going to, how do I do that? Okay, okay. So I'm going to assume 100 micron on the left and 100 on the right. So basically 100 on the left and 100 on the right. And let's sum this also. Control C, Control V. So let me sum this also. So 1827 into 2 plus 48. Okay, so this is 1827 into 2 plus 48, 36, 54 plus 48. 1827 into 2 plus 48 is 3702. 3702. 3702, right? Okay, so here I'm going to keep 100 on the left, 100 on the right. So, and here I'm not going to keep anything. So 3702 is what it's going to be. Okay, so that's what I'm going to do. Okay, so now I'll put here something at 0, and then I'll put here the dimensions should be 3640, 3650, 3750, 3850. So this will be 3850. So 3850 micron. 3850 micron. Okay, and then the height is going to be 3702, 3.702, right? And oh, I didn't even put that. How's that? Center. It will be 3850 and 3702. 3702. Okay, how come my what's the problem? The sketcher reported 4 errors, typically sketched orientation from clockwise to counterclockwise. Never saw something like that. Never saw something like that. Huh? Ah, hang on. Let me see if I'm recording. I'll find out the problem with this. Okay, let's continue. Okay, so I am going to pick a 0 point. Pick a 0 point here and insert. The width is 3850. 3850 and 3702. 3702. Say okay. So is that it? That's it. And extrude 9 micron. 9 micron. And this I will call as the ground plane. Done. Okay, so on top of this ground plane, I'm going to put a substrate. So again, the substrate is going to be height of 9 micron. So on the height of 9 micrometer, I am going to put here this guy, which starts at 0 and ends at the same number and has a height of 194, and this I will call as sub, and that's what it sits like, right? Yeah, so I'll say done. Okay, so I'll say we all. Now I'm going to draw the structure, right? So I'm going to leave 100 micron on the left. So I am on 194 plus 9, 100 and 203. 194 plus 9 is 203. 203 micrometer. Okay, so I'm going to draw on top of this surface, and I am going to draw a rectangle starting at 100 micrometer, which is 0.1 mm, right? 100 micrometer. Is that all I'm going to leave? 100 micrometer. Okay, later I'll extend it, doesn't matter. So this is 100 micrometer, or okay, 0.1 mm is 100 micrometer, right? And then I want to have here 3650 is the width, correct? And 1827 is the height, isn't it? 1827 is the height, correct? Say okay. So that's that. And here I am going to corners. I'm going to adjust the corners. Okay, so let's say 0.25 mm. 0.25 mm on the left and 0.25 mm on the right. Okay, so that's done, and then I want to put another one, which will be 285, 100. So it will be 100, 100 plus 285 is 385, 0.385. So this will be at 0.385. Okay, so 0.385. Okay, and it's going to have a certain width, and that width is 3650, and height is going to be 1497. 3650, 1497. 3650 and 1497. Okay. Oh, what happened here? No, wait, 3080, wrong. Okay, let's draw this again. Okay, 3000, so this will be 385, and it will be 3.080, 3.080. What? I'm drawing this 3,385. Say okay, and this one would be 3080, and the height will be 1497. Say okay. So I guess we are done with this, and this is going to be 9 micron tall. 9 micrometer tall. What has happened to this one? Why is it not drawing? Huh. Says solid body creation request profile as self intersection. Huh. Profile has self intersection. Oh, now I understand. Just one second. What do you mean by profile has intersection is this. Let's cancel this. So I need to cut this one out, cut this one out, cut this one out. What? Isn't it? Again, self intersection. Why there is a self intersection? And where is that self intersection? No self intersection. Okay. What I'll do is, okay, this is gone. Now, is that okay? It's not crying, right? It's not crying. Okay. Doesn't matter. Sometimes things are stupid. Okay, so what I'm going to do is I am going to just name this as outer. Done. Okay, and then I'm going to make another one. 2003. 203 micrometer. Okay, cross section. 3800 okay, 3080 and 1427. Okay, and the height is 9 micron, and I will call this as inner. Okay, so I have an outer, then I have an inner, and I do a subtraction of the two, so I have it. Okay, so then I have to repeat this on the top. So all I have to do is I have to copy this and create, modify, and reflect. Reflect about which axis? So this is u, this is v. So reflect about v, and that's there. And reflect about v. Oh, it went the other way. Where is the axis? Where is the rotation axis? Plane normal. A plane point. Okay, plane point is 0. So a plane point would be half of this. Half of this. So it will be half of 3,202. Okay, divided by 2. Divided by 2. 1851. Okay, so it will be 1.851, isn't it? So preview. So this will be reflection. Okay, so before even I do that, I'll make a copy of it. So this one, I'm going to say copy. Where is copy? Edit copy. And I will go here and say edit paste. Okay, so this will be called outer 2. Rename. Edit, is there a rename? I'll call this as outer 2. Correct? And this outer 2 I'm going to mirror. So transform, reflect. Okay, so this is going to be about this point, and this will be 1851. Okay, 1851. So that's done, and this gap happens to be, if this is exact, is this exact? Is this lined up? Yeah, done. Okay, view all. Okay, so this gap is 48 micron, isn't it? Let's check this from here. Come on, from here to here. It should be 48 micron. Why is it 45 micron? Okay, doesn't matter. Okay, so this gap, I'm interested in this gap. This gap is 48 micron, right? So this gap is 48 micron. That's fine. Okay, so now we are done with the geometry. Now I'm going to do the materials. So I'll go to add from the library. I'm going to add silver to it, and I'm going to add copper to it. So Ag is the silver, and then I'm going to add copper to it, which is Cu is the copper, Au is the gold, Cu is the copper. And then I'm going to add a new material definition, and I will call this as ferro A6S. And here I am going to double click it. Entry mode is loss tangent. This is going to be 5.92, and this is going to be 0.002. Done. Okay, so one more thing, appearance. I want to give this appearance to it, isn't it? Done. Done. Okay, so now copper is assigned to this one, and copper is assigned to this one, and then ferro is assigned to this one, and then silver is assigned to this one. Okay, so sorry. Okay, so this is our geometry. Now I'm going to add ports. I'm going to put in one port here, one port there. But before that, how about I extend these out by 500 micron more, isn't it? So I'll select this one and this, and I will say specify 500 micron. Half a mm is not going to do anything. Similarly, I'll do to this guy the same 500 mm. Done. So there's a gap now here. Same thing I'm going to do to this side. Done. And same thing I'm going to do to this side. And done. And say view all. And we are all set. Okay, so we are done with the design. I'm going to put the ports here. So to put the ports, say new waveguide port. You can cancel out. The definition is over here now. So I'm going to say port with no definitions. So this one is port 1. So this one is port 1, and this one somewhere in the mid. Come on. Okay. So here I'll make a correction. X location 2425, isn't it? 0 to 0, ठीक है. 2425. 425. Okay, done. And this is port 1. And this is a 50 ohm port. And the extent. Okay, so here this is along X 0.1. This F should make 0.1. Done. Okay, so this is port 1. And then this is port 2. Right? So port 2, I'm going to say insert no definition. So port 2, let's say somewhere here, and this one will take to the center automatically, and 36075 6075, that's done. And properties, this is port 2, and this is a 50 ohm port, extend use, and here I will do 3.75 and 75. Okay, so this is done. This is port number 2. Then I have port number 3 over there. This should give you a 10 dB thing, right? So this is port 3. Insert new definition, and this point somewhere, and this point would be the center, and this is 2425. This is going to be 2425. So this is centered now. This is port 3, and this is 50, and extend use sheet, and here it should be 2.2425. 2425. Oh, so this is 0.1. I thought it will invert that. Then okay, so this is port 3, and then the port 4. New, this is port 4. Come on, center. This is center. So this is 36075. 6075. That's that. That's centered. This is port 4. Port 4 is a 50 ohm port. Extent. This is 3.75, is it? And let's see that. Done. Okay, so we have got port 1, 2, 3, and 4. So if you look at top, this is port 1. So this one is port 1. Sorry. So this is port 1. That's port 2. The top one is port 3. And then that's port 4. Port 4 is going to be isolated. Okay, so once we are done with this assignment, I think we are all set for simulation. So I'm going to just save project, and I'm going to say coupler 10 dB 10 gigahertz, isn't it? Okay, and I'm going to create an Q simulation and go adaptive 9 gigahertz to 11 gigahertz 11 gigahertz, correct. And mesh refinement, advanced convergence solver, direct iterative, and anything else, frequency meshing solver, create and Q simulation. If everything is okay, we should be able to get the results, and if something is wrong, I have to recreate the video. Let's see. Okay, so it's going to mesh at 11 gigahertz. Okay, and delta S is going to show up as 0.05. So it has to do 0.01. Okay, 0.4. Am I recording? Yes, I'm recording. I don't have much time left. Hopefully this should work. If not, what can happen is that the coupling can be stronger. but the impedances should be matching, isn't it? So now it's solving it. I'm interested at 10 gigahertz. What happens? Okay, it's done. Let's go and see the results. So in the results, I'm interested in S parameters. S parameters. I'm interested in S11 on a Smith chart. So I'm going to put here a Smith chart. I'm interested in S11. Oh my God. S11 is way up there. 2 is on the same. 3 and 4 all up there. Okay, so impedance has to be reduced. Okay, fine. So now I'm going to look at so S11 is that. So let's look at S331. Not here. Okay. So I want to look it on a rectangular graph. S11, S22, S33, S44, S31 around 10-11 dB. Okay, what does it say? S31 is around 11 dB or to 12 dB, isn't it? 1331. Yeah, let's just remove all of this. Okay, I am interested in only 31 and 31 and 13. They are 11 dB of coupling. And let's also look at 41. 41 is 21 dB down. So this is going to be isolated port. The coupling has to be made stronger and the impedance has to be adjusted. Okay, so I'm going to do 1 or 2 iterations to this. Okay, so first thing first. So this time I'm going to keep you along with me so that you see what is going on. Okay, so I am going to take this and reduce the, so impedance is less, right? So I'm going to move this one, okay, by 10 microns. So I'll say minus 10. Okay, so I have moved this minus 10. Fine, so same thing I have to do on this side. So this one I will also do minus 10 on this. Okay, so this is reduced by minus 10. So now this is going to be 320. So let's hit the simulate button again. So you see how quickly this helps you do this stuff. Okay. So let's see what happens. Otherwise, I'll put you on pause and then I'll explain you what I did. Let's see if this brings closer to 50. So meshing is done. Almost. Hang on a second. Almost done. Okay. Let's simulate the frequencies. Okay, we are done. Let's look at the results. And my interest is in S11. Directly I'll approach S11 on a Smith chart. On a Smith chart, I'm interested in S11. Still over there. 2, 2, 3, 3, 4, 4. And let's see this in terms of rectangular. So has it improved? Slightly. Okay. Slightly it has improved. So notice this is 10.5, right? And what happened to 3.1? it has also improved a little. So if I improve this matching, then this coupling will improve, right? Okay, so let's do few more iterations. Okay, so what I'll do is, if I go under geometry, modeling sequence, offsets, specify offsets, I can do this as 20 and done. Right. Hey, offset minus 20, right? Similarly, modeling sequence here, offs, apply, and over here I am going to look at offset minus 20. So that's done. Okay, so we are done. I'm going to save it and run this again and create in Q simulation. So now if this doesn't come closer, we have 11.8, right? So I will put you on a pause and then adjust it and come back. Okay, so if this doesn't work, I'll put you to pause and I'll quickly adjust this and come back and show you the final results. It's 11.8 minus 11 point something, right? Return loss. Let's see again. Results, simulation number 3, S parameters, and go to Smith, look at S11, or go to S33, S44, go to X5 chart. So this is better than now. This is better than 11 point something. So we are going in right direction. And if I look at S31, this is coming up, right? So I'll put you on a pause. Okay. Okay, so I'm done with the final one. I'm not going to spend more time on this one. Okay, what I've done is the offset which I was doing, reducing the width of the line. I've reduced the width by 100 micron on both the branches, right? So let's see the effect. So this was the 7th iteration, and I'm going to look at S11. So S11 is over here, S22, S33, S44. In terms of XY graph, this is going to be better than 17 dB return loss. So I will say file, save as, and can I just save marker, save plot as CSV, save plot to graph. Okay, and here, okay, I have saved this. So I have saved this as my return loss. Okay, return loss across 9 to 11 gigahertz, and it is better than 17 dB. The next graph I'm going to plot, the next graph that I'm going to plot is going to be the coupling S31, right? And this S31, okay, don't want a dotted line. So axis graph, where is the line thing? They have changed the GUI, the line thing. This is the graph properties. This is their solid line, and wait. Okay, done. Okay, so this is going to be file. So I'm going to just file, save as, save to graph, a new graph. So this one is okay. So this one is basically your what you call coupling, And on the same graph, I am going to put the isolation. So that's the isolation, and I'm going to edit this one. So I'm going to make this one as red color, okay, and I'll give a weightage to it. Okay, so I'm going to say file, plot to graph, create a new graph. Okay, so I have 3 graphs to show you, okay, for this design. One is your return losses. These are the 4 return losses, okay, and they are better than 17 dB. Okay, next I want to show you, why am I stuck here? Sometime it freezes. Okay, I'll have to put you on a pause. Right, I had to put you on a. Okay, so very quickly I'm going to show you everything on a single graph. Now S21 is a through. A through line is like, you know, 0.6 dB to 0.95 dB. So that's the through line from 9 to 11 gigahertz, right? Then I have got the coupling of minus 10 dB, right? So at 9 gigahertz is minus 10.4. At 11 gigahertz is 9.6, and somewhere between I have 10, right? Then the return losses are better than 17 dB, right? And then finally the green curve which you see here is at 9 gigahertz 24 dB isolation, and at 11 gigahertz 23.5 dB isolation. So this is how the coupler is working. Now very quickly I want to show you the surface, what you call the surface currents. Okay, so I want to look at the current densities, and I want to excite port 1, and I'm going to do this as 10.3 gigahertz. And what else? And legend, I am going to edit its properties, and 0.5, let's say 0.5, and with the 0.5 I say apply, done. And over here I say this and say play. Okay, so nothing is happening. The current densities, okay, I haven't chosen which ones to plot on. So I haven't chosen, I want to look at copper and this. Okay, so that's done. And let's look at the legend first again. Properties, let's say from 0, okay, to this. And say done, and I want to make this one invisible. So this one is not invisible. Opacity. Okay, opacity works. So this is the opacity of the substrate. Okay, so this I want to show you. So this is port 1. I don't know. Yeah, this is port 1. Correct. And let's change the legend. Okay, this is 0.8 and say done. Okay, so let's go here and show you what this coupler is doing. Okay, so I am going to say plot, print it, play it. Okay, so which port is the input port? Okay, so this is my input port, and this is my isolated port, this is my coupling port, and this is my through port. And I'm going to adjust the legend again. Properties, let's say 2 amperes, and say done. Okay, so you see that the power is going to go from port in into, let me adjust the legend once more, and let's make this as 4. Done. Okay, and pause this and set up and find and sequence and play. Okay, so what you're seeing here is you are putting in power into port 1. It is going to go to port 2, and a part of it is coupling to port 3, while port 4 is silent. Right, it's green and blue. Let me adjust this again once more. 5. Say done. Okay, so you can see the direction of the arrows also. This will give you an idea. So I'm going to put in power from port 1. It's going to go to port 2. and a part of it is coupling, which is 10 dB down to port 3, and then the port 4, if you over here, is silent. You see it's blue color. Even I can even further go to adjust the color scale to 8. Done. Yeah, now it's better. Okay, so power is going from 1 to 2, a part of it is coupling to 3, and then the remaining port number 4 is silent over here. Nothing's going to port number 4. So I think this is a directional coupler design at 10 gigahertz, right? So you can see how this is working. So, and you can also see what is in the ground plane, right? So 1 and 2 are through ports. Okay, so I am going to, let's see if I captured the last part. Yeah, so I'm going to stop here. It has been a long video. Thanks a lot.